Hello everybody and welcome to your linear algebra review on the introduction of elementary matrices. My name is Jason and I work for the ASU Tutoring Centers. Now before we talk about elementary matrices, let's recall what elementary row operations are. So remember there are three elementary row operations. Elementary row operations. I'm just going to say ops. So remember there are three of them, right? The first one is that we can swap two rows. So given any matrix A, we can swap any of the two rows. The second one is we can multiply a row by a non-zero scalar. And the third one is that we can add a multiple of one row to another. So we can add multiple of one row to another. Okay, so these are our elementary row operations. Now what an elementary matrix does is it mimics these operations, except instead of just doing the operation, so instead of just saying, hey, this happens, we can actually do it by multiplying by a matrix. So instead of just swapping two rows, we can actually find a matrix to multiply by that'll do that swapping. So it's sort of like you see what's happening behind the scenes. Instead of just doing the action, we can actually physically see a matrix that does that action for us. So let's look at some examples. So imagine you have some arbitrary matrix. I'll call it A, and it'll be A, B, C, D. Okay. So let's look what happens when we swap two rows. So imagine I took my matrix A, B, C, D, and I swapped row one with row two. Row one, I'm swapping with row two. So I would get C, D, A, B. Now, if we wanted to mimic that using an elementary matrix, what we would do is we would take our original matrix, A, B, C, D, and our goal is to get this guy out of it, C, D, A, B. So the question is, what can we multiply our matrix by so that we get this matrix where we swap the rows? Well, all elementary matrices, and this is big, so I'm gonna put it up here. All elementary matrices come from the identity matrix. So if you wanted to know how to swap the first two rows, what you want to do is you want to think of the identity matrix. So remember the 2 by 2 identity matrix looks like this, 1, 0, 0, 1. Imagine doing that operation of swapping the two rows on the identity. What you would get is you would get 0, 1, 1, 0. So in fact, if you take this matrix and multiply by this matrix, you get this one out of it. Okay, you can verify that. You can do the multiplication out and you'll see that you'd get that matrix. So instead of just saying, hey, let's swap two rows, we can actually say, hey, let's multiply by this specific matrix and that'll mimic us swapping two rows. Okay. So all elementary matrices, you can think of them as coming from the identity matrix. Cool. So let's look at the next example. What if we wanted to multiply the first row by some constant, let's say alpha? We want to multiply the first row by alpha. We have alpha A, alpha B, C, D. Okay, so we're going to go through the same process here. We're going to say, okay, what do we need to multiply our matrix by? So we're starting with the matrix A, B, C, D. What do we need to multiply by so that we get alpha A, alpha B, C, and D? Well, again, let's think of the identity matrix, 1, 0, 0, 1. Imagine multiplying the first row by alpha. We'd have alpha 0, 0, 1. And you can verify if you take this and multiply by that, you end up getting this. So the elementary matrix that corresponds to multiplying rows by non-zero constants looks like this guy. We just multiplied the first row by alpha. Okay, we have one more. Imagine we have the matrix A, B, C, D, and we want to do row 1 plus alpha row 2. We want to multiply row 2 by some alpha, and we want to add that to row 1. So we have A plus alpha C, B plus alpha D, C, and D. So same process here, right? We have A, B, C, D. We want to know what we need to multiply by. Whoa, getting kind of small. Running out of space. Oh, that shouldn't be a B, that should be a C. So again, we're like, what do we need to multiply by so that we end up getting this matrix out of it? And it's again, it's a similar process. Imagine trying to do that to the identity matrix, okay? And remember how matrix multiplication works, right? We multiply rows by columns. So if we wanted to get this row times this column to equal A plus alpha C, what do we have to do? Well, we'd want 1A and we'd want alpha many C's. And then we don't want to change the bottom row, right? The bottom row, the C and the D, we want that to stay the same. So we would leave this bottom row as the same. And you can verify if we do the multiplication here, oopsies, we end up getting exactly what we wanted. So this is what the elementary matrix looks like that corresponds to adding multiples of one row to another. You say, what row am I trying to change? I'm trying to change row 1. So I'm going to be changing row 1. And how am I going to be changing it? I'm trying to add alpha many R2s. So I'm going to put alpha in the second column because we're trying to add the second row. And remember, matrix multiplication goes rows times columns. Okay? So these are your elementary matrices. So if we were to just sort of generalize, if you wanted to look at what adding or swapping two rows looked like, your elementary matrix would look like 0, 1, 1, 0. That would swap the first and second row. If you wanted to multiply the first row by alpha, look like that one. If you wanted to add the multiple of another of the first row, if you wanted to add alpha multiples of the second row to the first row, it would look like this one. So these are what your elementary matrices look like. And of course, these aren't the only ones. There's tons of elementary matrices out there. You know, what if we had 3 by 3s? Then it's a whole world. Well, we're going to be sort of dissecting those throughout the next few problems, okay? So let's go ahead and take this question. We're trying to find a series of elementary matrices to convert the following system to reduced row echelon form, okay? So let's take our system, 4, -2, -3, 2, augmented with -2, 5, and let's do the row operations, okay? So what would the first row operation be if I wanted to get this in reduced row echelon form? Well, I'd want to make that a 1, correct? So I would take 1/4 row 1. If I'd multiply by 1/4, that would be 1, -1/2, -1/2, -3, 2, 5. Okay? So that's us doing the elementary operation. But now let's find what elementary matrix this corresponds to. I'll call this E1, my first elementary matrix. And what would it look like? So what did we do? We just took the first row and multiplied by 1/4. So the elementary matrix that looks like is 1/4, 0, 0, 1. We just take the identity matrix and multiply that first row by 1/4. That's our elementary matrix. Okay? So if we were to multiply this first row by 1/4, this is what that elementary matrix would look like. Cool, what's our next step? Well, we want to get a 0 in the bottom left position, right? We would go ahead and we would take row 3, sorry. We would take row 2 plus 3 row 1s. What would that look like? Well, our first row is unaffected. We would do that plus 3 of those is 0. That plus 3 of those is 1/2. And that plus 3 of those is 7/2. Okay. So let's ask ourselves, okay, what elementary matrix would that correspond to? So we're trying to change the second row. So the first row is going to stay the same. The second row is what's changing. And how are we changing it? We're taking 1 of row 2 and we're adding 3 of row 1s to it. So remember, when you do matrix multiplication, it's rows times columns. So think almost like this first column affects row 1 of your matrix, and the second column affects row 2 of your matrix. So it's rows times columns. So we're taking 3 row 1s plus 1 row 2. Okay? So you can think about that. What will be the next step? Okay, we need a 1 in the bottom right position to get into a reduced row echelon form. So we're going to go ahead and multiply row 2 by 2. So row 1 is unaffected. 0, 1, and then 7. So what do? We multiplied row 2 by 2. So we take our identity matrix and multiply row 2 by 2. We have one more step. I'm kind of running out of space, but that's fine. I'll just do it down here. We need to get a 0 in the top right position. So we're going to go ahead and take row 1 plus 1/2 row 2's. So we get the identity over here. Row 1 plus 1/2 row 2. So -1/2 plus 7/2, that's 6/2, which is 3. Cool. And then what does that elementary matrix look like? Totally running out of space. I'll put it in the top right position. So I'll call that E4. So what did we do? We took row 1 plus 1/2 row 2. So we're changing row 1. So row 1 is going to look different. Row 2 is going to look like the identity. And how are we doing it? We want 1 many row 1's and we want 1/2 many row 2's. So these are our elementary matrices. And if you really want to check, if you really want to verify, you could see if we started with this matrix 4, -2, -3, 2, augmented with -2, 5, and you went and did the matrix multiplication. So if you multiplied this by E1, and then you multiplied by E2, and then by E3, and then by E4, you would end up getting this matrix over here, 1, 0, 0, 1, augmented with 3, 7. So there's a way you can check your work. And look at the order that we did the multiplication in, right? Because the order of matrix multiplication is important. We multiplied by E1 first, so that's the one that's closest to our matrix. Then after that, we multiplied by E2, and then E3, and then E4. So that's why it's sort of in that like backwards order. Cool. So that's what elementary matrices are. That's how you find them. That's what they look like. And in the upcoming videos, we'll see why they're particularly important. Wonderful. All right. Well, as I mentioned at the beginning, I work for the ASU tutoring centers. So if you want to see what kind of free resources we have that we offer on all 4 major campuses and online, please check out tutoring.asu.edu. If you want more videos that are like this, that go over specific concepts from your course, or maybe you want to see what upcoming review sessions we have for the exams in your course, go ahead and check out this link down there. Thank you all for joining me, and have a fantastic day.